Welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had looked at the PAPR problem in OFDM systems, that is the peak to amplitude power ratio problem in OFDM system. What we said was the information symbols capital X0, X1, X2 so on correspond to, let us say, BPSK modulated symbols plus or minus A, plus or minus A, plus or minus A. Before we load these information symbols onto the subcarriers and perform an FFT. So, the actual transmitted samples X0, X1, Xn minus 1 correspond to the IFFT of these information symbols. Hence, what essentially happens is, when you look at this, we have a peak to average power ratio that increases with the number of subcarriers, and that is as the number of subcarriers increases, the peak to average power ratio increases. And why is the peak to average power ratio increasing? Because we said the high peak power rises from the IFFT that is being performed in OFDM, which can occasionally result in a high peak value signal. So, because these signals are being combined in the IFFT, or the symbols are being combined in the IFFT, they occasionally produced a high peak value signal, which is significantly deviating from the otherwise the mean value of the signal. Hence, the peak deviation is much higher over the mean. That results in a high ratio of peak to average, high peak to average power ratio in an OFDM system. And we also saw that the peak to average power ratio can be measured by the CCDF, that is the probability that the peak to average power ratio is greater than a certain threshold. We also looked at examples for different of how the PAPR CCDF curve looks for different numbers of subcarriers. Now, what is the ill effect of PAPR? We said PAPR causes distortion in an OFDM system, since every OFDM amplifier has a certain linear range which is biased about the mean. Now, if the deviation about the mean is significantly large, that is the peak value occasionally significantly deviates over the mean, then this amplifier crosses over into the saturation or the non-linear range, but its amplification is not linear anymore. Now, when the amplification is not linear, that results in distortion, and that results in inter-carrier interference, that results in a loss of orthogonality amongst the different OFDM subcarriers, which results, as we saw in the case of carrier frequency offset, results in a decrease in the net SNR. Okay? And if we look at a solution, how can we expect to solve this PAPR? The solution, we said, is to use single carrier FDMA, and that is as follows. That is, if you observe the OFDM transmitter schematic, if I introduce an endpoint FFT before the endpoint IFFT, the FFT and IFFT cancel, and this reduces to a single carrier system, right, which PAPR is very low, it is almost close to 0 dB, that is what we said. Okay. Hence, what I want to do is I want to introduce an FFT block before this IFFT. However, I do not want to do an endpoint FFT, because that will go back to the single carrier system and intersymbol interference. I want to do something in between the single carrier system and essentially OFDM. So, I am going to choose an FFT size m, which is much smaller than m, and then map these m symbols onto n subcarriers. Hence, the net schematic looks as follows. I take this m point FFT m symbols, perform their FFT, map them to the subcarriers, and after I map them to the subcarriers, I can now perform an endpoint IFFT. Here I will perform an endpoint IFFT. Here I will perform an endpoint IFFT, and the rest is exactly like we had earlier, which is out of this endpoint IFFT, I will serialize it, that is, I will convert from parallel to serial, that is a multiplexing operation. Once I multiplex these signals, I will then add the cyclic prefix and transmit these. I will add the cyclic prefix and then transmit these samples. So, these are the transmitted samples, and if you look at this, these are the two new blocks that we are talking about. If you are looking at this, the rest all are conventional OFDM blocks. These are the two new blocks in SC-FDMA, that is, these are the endpoint FFT and the subcarrier mapping. These are the two new blocks that we are adding in SC-FDMA. And we also said that the number of symbols in the endpoint FFT, number of symbols M in the FFT is much smaller than N, which is the number of subcarriers. Okay, so, the number of symbols M in the FFT is much smaller than N, because if M equals M, we are going back to a single carrier system and we do not want to do that. So, M, which is the number of symbols in the FFT, is less than N, and this is M point FFT is introduced for the purpose of reducing the PA PR in the OFDM system. After the DF, and this step reduces, hence introduction of this M point FFT significantly reduces the PAPR. Of the M point FFT in SC-FDMA significantly reduces the PAPR of the system, and this is essentially this is essentially the technology, this is essentially the SC-FDMA scheme, which is single carrier FDMA. Hence, this is the basis SC-FDMA, where SC-FDMA, as we have talked about, stands for single carrier frequency division this stands for single carrier frequency division for multiple, this stands for single carrier frequency division for multiple access, and this actually reduces the PAPR, that is the peak to amplitude power ratio of the OFDM system. How does the SC-FDMA receiver schematic look? We have looked at the SC-FDMA transmitter schematic. So, now what we want to do is we want to look at the SC-FDMA receiver schematic. So, I want to look at the SC-FDMA receiver schematic, and that SC-FDMA receiver schematic looks as follows. What we want to do is we want to essentially add the receiver similar to OFDM. Once I get the symbols, what I am going to do is I am going to remove the cyclic prefix and followed by I am going to do a serial to parallel demux operation, that is serial to parallel demultiplying. That is, I am going to block this, I am going to block into the original FFT size, which is the original IFFT size, which is n subcarrier. So, I am going to have similar to what I had earlier, I am going to have n subcarriers over which I perform n point FFT. So, here I am going to perform n point FFT. Now, after I perform the n point FFT, what I am going to have to do is I am going to have to equalize these symbols. Previously, remember we had a detection, but before detection now we have to equalize, because this is single carrier system. So, we have to equalize and then we have to do a equalize across each subcarrier and then we have to do a demapping. So, this is equalize and now do a demapping back to the M symbol. So, now we have to do a subcarrier demapping, and once we demap back into the M. We demap into M symbols and now we perform the M point, we perform the M point FFT operation. After we perform, we perform the N point IFFT operation, and after we perform the M point IFFT operation, I can serialize this, and so I convert from parallel to serial, which is essentially I multiplex this into the data stream, or essentially the symbol stream. So, this is how the SC-FDMA receiver schematic looks, that is cyclic prefix removal, serial to parallel demultiplexing. This is same as in OFDM, endpoint FFT. Now, I have to equalize and demap, remember, into the M symbols. So, I equalize, demap, perform the M point IFFT, multiplex it, and I get back my symbol stream. So, if you look at this, these are again the two new blocks that we introduce in the SC-FDMA receiver schematic. These are the two new blocks that we introduced in the SC-FDMA receiver schematic, and then I get back my symbol stream. So, it incorporates two new blocks essentially. So, this SC-FDMA receiver schematic incorporates two new blocks compared to the OFDM, After the N point FFT, the symbols are equalized. So, first N point FFT, the symbols are equalized across all subcarriers, then they are subcarrier demapped. following the above operation, they are subcarrier demapped. This is essentially inverse of the mapping operation that was done at the transmitter. Remember earlier in the OFDM transmitter schematic we had a subcarrier mapping operation, now we have a subcarrier demapping operation at the receiver, and finally the IFFT is carried out and the serial symbol stream is generated. Finally, the M point IFFT is performed and the serial symbol stream finally the M point IFFT is performed and the serial symbol stream is generated. So, if you look at this, first after the N point IFFT these symbols are equalized across subcarriers. After equalization they are demapped to the M, demapped from N to M subcarriers. After the demapping they are again, you perform the M point IFFT to reverse the M point FFT operation of the receiver, and then you give back the serial symbol stream and the serial symbol stream is again generated. All right. So, that is how the serial symbol stream is generated, and there is one last aspect that we need to talk about in the in this SC-FDMA system, which is essentially the subcarrier mapping operation. How are these subcarriers mapped at the SC-FDMA transmitter? So, we want to talk about the subcarrier mapping. How are these subcarriers mapped in a SC-FDMA? If I look at a subcarrier mapping operation, then what I am looking at essentially is, let me go back again to my SC-FDMA transmitter schematic. I have an incoming stream of, I have M symbols x0, x1, so on up to x small m, which I am mapping to capital M so I am performing here I am performing the M point FFT, and the M point FFT yields me, which I am now mapping to the capital N subcarrier. So, here I will have x0 up to xm, which I am mapping to N subcarrier. So, here I am performing subcarrier mapping, and I am subsequently performing the N point IFFT. Okay, I am performing the N point IFFT. So, the essential idea is, how are we mapping from these capital M to N subcarriers, M to N how are we mapping these subcarriers? This we can illustrate by, so the subcarrier mapping is a key operation. So, the subcarrier mapping is actually a key operation in SC-FDMA. Let us illustrate this for a certain example. So, as a simple example to illustrate subcarrier mapping, what I am going to do is I am going to consider, for example, as an example scenario, consider m equals 4, that is the size of the m point FFT, that is I am going to consider m equals 4 and n equals 12 n equals 12 subcarriers, which means I have x0 4 information symbols x0, x1, x2, x3. I perform the m point FFT, which is essentially the 4 point FFT. These are x0, x1, x2, x3. So, these are the symbols that are now to be loaded onto the N12 subcarrier. So, these 4 symbols need to be loaded onto 12. These 4 symbols need to be loaded onto the 12 subcarriers, and this can be done as follows. For instance, what can we do? One way to do this is, so I have 12 subcarriers. So, how am I going to? So, I have 12 subcarriers. I can load x0s as follows. I can load x0, 0, 0, x1, 0, 0, x2, 0, 0, x3, 0, 0. So, these are the 12 subcarriers. And I am, remember, look at this, I am interleaving the zeros with the symbols. So, these are, I am interleaving zeros. This is termed as interleaved FDMA. FDMA or essentially IFDMA. Alright. So, one way to load these 4 FFT symbols onto the 12 subcarriers is to interleave them with zeros. I have namely 1 symbol, 2 zeros, 1 symbol, 2 zeros, 1 symbol, 2 zeros, 1 symbol, 2 zeros, and so on, and now perform the endpoint IFFT. This is known as interleaved FDMA. Another way, another simple way, as we all know, is of course to simply do a zero padding operation, that is 1, 2, 3, 4, 5. So, I have again 12 subcarriers. What I can do here is I can load them onto the first 4 subcarriers and leave the rest of them 0. This is essentially zero padding based subcarrier mapping. This is zero padding based subcarrier mapping in SC-FDMA, and this in fact is known as LFDMA. This scheme is termed as LFDMA, and in fact this is the scheme that is used in the uplink of the 3GPP, that is the 4th generation standard LTE. This is used in employed in uplink of LTE, which is the 4th generation 3GPP. Hence, there are two techniques. One is to interleave the zeros. This is termed as IFDMA. The other is to zero pad. This is termed as LFDMA. In fact, this is used in LTE, which is the 4th generation wireless communication standard. So, this brings us to the conclusion of the section on OFDM. Hence, let us now summarize the different modules that we have seen in OFDM. So, now let us look at the summary of the OFDM modules, that is summary of what we have seen in OFDM so far. So, in OFDM, starting with the first thing we have seen is multi-carrier modulation, which forms the basis for OFDM. So, we started with multi-carrier modulation, which forms the basis for OFDM. Second, we saw OFDM itself. This leads to OFDM, which is results from the sampling of the MCM signal. This we said sampling of MCM signal. This is nothing but stands for orthogonal. OFDM stands for orthogonal frequency division multiplexing. Then we looked at the concept of cyclic prefix. We looked at the concept of CP or cyclic prefix. We also looked at an example, a practical example of OFDM. This related to the fixed profile of WiMAX, which is the 4G wireless standard with 256 subcarriers. So, we looked at the fixed profile of WiMAX. This had n equals 256. This had n equals 256 subcarriers, and then we looked at an important aspect, that is MIMO OFDM, which is essentially multiple input multiple output OFDM. That is, this is essentially OFDM for multiple input multiple output system. So, this is essentially OFDM for multiple input multiple output systems. Then we looked at distortion in OFDM systems. We looked at distortion in OFDM systems. Namely, we looked at the problem of carrier frequency offset. offset or CFO which arises in OFDM. This is a serious problem, we said, because this results in loss of orthogonality amongst OFDM subcarriers, thereby introducing intersymbol interference, intercarrier interference. Thereby introducing intercarrier interference. The next, we said, another important factor that needs to be considered in OFDM is the PAPR in OFDM systems, where PAPR stands for peak to amplitude. PAPR stands for peak to amplitude power ratio in OFDM, and this also we said causes saturation in amplifiers, causes saturation in amplifiers, resulting in nonlinear behavior of amplifiers in the OFDM system. So, that is the problem of PAPR, and we said to tackle the problem of PAPR we can use SC-FDMA, that is SC-FDMA, which stands for single carrier this stands for single carrier frequency division for multiple access. This can be employed to tackle PAPR issue in OFDM. We said single carrier FDMA can be employed to address or can be employed essentially to tackle the problem of peak to amplitude power ratio, that is the problem of high PAPR, high peak to amplitude power ratio in OFDM systems. So, with that we come to the conclusion of the OFDM module, and now we want to start a new module which essentially relates to channel modeling in wireless systems. So, the next model we want to talk about, or the next module we want to talk about, is essentially wireless channel modeling. This is the next topic that we want to talk about, and we know already from our basic knowledge of RF propagation that the wireless signal strength decreases with increasing distance. So, we know that wireless signal strength decreases as the distance of propagation we know the wireless signal strength decreases as the propagation distance increases. For instance, if you look at a base station and a mobile, and we look at the distance d between the base station and the mobile. In fact, we can also look at the straight line distance d between the base station and mobile. We would like to predict, we would like to find the signal strength required at the base station to receive a signal at the mobile, at an intelligible signal at the mobile at a distance d. Hence, what we would like to do, we would like to characterize the signal at the mobile as a, we would like to characterize the signal strength at the mobile as a function of d. And these, since we need models which predict the mean signal strength as a function of the distance between the transmitter and receiver for essentially the design of a cellular system. Hence we need models which predict the mean signal strength, which predict the mean signal strength at the receiver as a function of the separation between transmitter and receiver. Hence, we need essentially need what you want to do is want to build models which can actually essentially characterize the signal strength at the receiver as a function of the separation between this transmitter, which is the base station, and the receiver, and same when the mobile is the transmitter and the base station is receiver. We need models which characterize the signal strength, so that we can characterize the transmit power, so that we can characterize the receive power, and so on. And these models are essentially termed as propagation models. Hence, these models are termed as channel models or large scale propagation models. These models are termed as large scale these models are termed as large scale propagation model. We will start looking at some of these propagation models to characterize the received signal strength in a wireless communication system. So, let us start with the basic model, which is the free space propagation model. So, I want to start with the basic model, which is essentially the free space propagation model. The free space propagation model, it predicts the received signal strength when there is an unobstructed path between the transmitter and the receiver. So, the free space model predicts the received signal strength when there is an unobstructed, remember this is the key, which is essentially when there is an unobstructed path between, there is an unobstructed propagation path between the transmitter and the receiver. There is an unobstructed propagation path between the transmitter and the receiver. This is governed by the Friis free space equation. This is governed by the Friis free space equation, where the received power as a function of d, Pr, that is the received power as a function of distance d is given as Pt Gt Gr lambda square divided by 4 pi d square L, that is the received power Pr as a function of d is given by Pt Gt Gr lambda square divided by 4 pi d square L, where each of these quantities is defined as follows. Pt is nothing but the transmitted, this is the transmitted power, Gt is the transmit antenna gain, Gr is the receive antenna gain, and lambda is nothing but the wavelength. This is the wavelength, which is equal to C over Fc, where Fc is the carrier frequency, and this d, of course, d is the distance, and this L is the system, L greater than equal to 1, this is nothing but the system loss factor. So, it is given by the transmit power times the transmit antenna gain times the receive antenna gains times lambda square, where lambda is the wavelength, divided by 4 pi d square, where d is the distance and the system loss factor. Alright. So, this is essentially what we have as the expression. So, this is our expression that we have basically for this received power as a function of this. This is nothing but the Friis free space equation. Let me just write this again. This is nothing but the, this is the Friis this is nothing but the Friis free space equation. And now we can simplify this as follows. Let us consider, let P naught be the power received at a reference distance d naught. Let P naught be the power received at a reference distance d naught. Then we have P naught equals Pt Gt Gr lambda square divided by 4 pi d naught square L, implies, if we consider P naught d naught square, that is equal to Pt Gt Gr lambda square by 4 pi square L. that is equal to 4 pi square L. Hence, for any distance d, what we have is P received as a function of d equals Pt Gt Gr lambda square divided by 4 pi L into 1 over d square, and this is what we already saw is nothing but P naught d naught square. Hence, this is equal to P naught d naught square by d square. That is, the power received at any distance d is some constant which is P naught d naught square, that is reference power P naught received at distance d naught divided by d square, and this factor actually d square is the most important one, that is it shows that the power decreases as the square of the distance, and this factor 2, this power 2 is known as the path loss exponent. Shortly we are going to see how the path loss exponent differs. It's nominally it is 2, but path loss exponent in urban regions can be greater than 2. In fact, it lies usually between 2 and 4. All right. Hence, one small last step, which is we want to convert this received power in dB, convert received power to dB. We have P dB is nothing but 10 log 10 P, which is equal to 10 log 10 P naught d naught square divided by d square, which is essentially 10 log 10 P plus twice into 10 log 10 d naught by d, which is essentially P naught dB, that is reference power in dB, minus 20 log 10 d by d naught. So, P in dB, this is the free space received power in dB this is the received power in dB in free space, and we saw that for free space path loss exponent is 2 for free space. However, in cellular environments, in urban cellular environments, as you saw in the very first lecture, there is a dense clutter, there is a lot of scattering, there is a lot of reflection, hence there is rarely free space propagation. All right, there might be a line of sight, but there are also several reflected and scatter paths. In such scenarios, we see that the path loss exponent can be greater than d square. In general, the path loss exponent can be between 2 and 4. We are going to see an example of this. For instance, let us consider the ground wave reflection scenario. So, let us, as an example to see how the path loss exponent can be greater than 2, let us consider a typical ground reflection let us consider a typical ground reflection scenario. The ground reflection scenario can be modeled as follows. I have a transmitter at a height t and I have a receiver at a height hr. So, ht is the height of the transmitter, hr is the height of the receiver. Now, there is a direct path between the transmitter and the receiver. This is the line of sight or LOS path between the transmitter and receiver. There is as well also there is also another path which is a reflected path. So, this path is essentially the ground reflected path, such that the angle of incidence theta I and angle of reflection are equal. The angle of incidence and the angle of reflection are equal. Let me call this distance as the line of sight distance, and let me call this distance as the ground reflection distance. You can see that both these distances are different. And we said HT, this is nothing but the height of transmitter, that is, let us say something like height of the base station in our cellular system, and this is height of receiver, that is the height of the person who is talking, or maybe if he is on a building, the height of the building, and so on. And so, we have two paths now. We have one is the LOS path, let us say the field along at the receiver along this path is EOLOS, and the field at this path, let us say, is EG, which is coming from the ground reflected path. Further, let us denote this distance, horizontal distance between the transmitter and receiver, by D. This is nothing but, this is essentially horizontal distance between the transmitter. So, this is the horizontal distance between the transmitter and the receiver. So, that is what we currently have. Hence, what we observe is that we have two propagation paths, one is the direct path, one is the reflected path, one is the line of sight, one is the reflected. Hence, the total received signal is nothing but E total, which is equal to E line of sight plus E ground. This is again from the line of sight path, and this is from the ground reflected. This is from the line of sight path and the ground reflected path. Now, each signal E naught, first for instance, let us look at the line of sight path, that is some E naught, let E naught be the reference strength at some distance D naught. Remember, the power decays by distance by d square in free space, which implies the strength, the signal strength decays by a factor of d. Hence, this is some E naught D naught by d, and then there is going to be a, in fact, this is d LOS, and there is going to be a phase factor that is essentially arising because of the propagation distance. So, in this what we are saying essentially that E naught is strength or the field strength at distance d naught, that is some constant. Okay. DLOS is the propagation distance. Remember, this is the line of sight, DLOS is the line of sight propagation distance or propagation distance of LOS path, and this we are saying is the phase factor arising in the carrier due to the propagation. This is the phase lag of the carrier at receiver arising due to propagation delay. Now, what I am going to do is I am going to use an approximation. I am going to set this DLOS in the denominator as approximately equal to D. Hence, I am going to use the approximation that this is approximately equal to E naught D naught divided by D E times j 2 pi f c T minus DLOS by C, where I have approximated DLOS, that is the line of sight distance, for the signal strength by D, because the major effect of the propagation distance is in the phase factor. The effect on the signal strength is not very significant. So, due to the so because of shortage of time, I have to end this lecture here, and then again we are going to start from here and continue with this in the next lecture. Thank you very much.